Hello there, Mr. Sutton here, bringing you this Pre-Cal Honors 4-6 lesson on exponential equations. In this one, we will be learning how to solve exponential equations. We should probably start by defining what an exponential equation is. This is an equation where we have a variable in the exponent. It's not enough to just have exponents. The variable has to be in the exponent, like in this equation here, where this x is inside exponent land. So as a warm-up, see if you can figure out how to solve this. All right, let's see what we came up with. Now, just intuitively, if we have 3 to something equaling 3 to something else, you have the same base, you have an equals, that means the exponents must have the same value. So what we can do in a situation like this where we have the same base on each side is we can cancel that base. Kind of like when you had the same log on each side, you could cancel the logarithms. So those 3's, we can get rid of them, and then 4x and 8, we can bring those down as just a normal equation. And then x is 2. So that method we just used on the last example is called the common bases method of solving equations, and it only works if, you guessed it, you've got a common base. In this problem, we do not have a common base. However, sometimes it is possible to rewrite things with a common base. So pause the video, see if you can figure out what the common base is here, what are 625, 125, and 1 over 25 all powers of, and rewrite it with that base. Did you figure it out? These are all powers of 5. 625 is really 5 to the 4th power. And when we rewrite it like that, whatever is not part of the actual base, we're going to put outside of a parentheses, just so we can keep separate what used to be the base and what used to be the exponent. 125, that's really 5 to the 3rd. And then 1 over 25, well, 5 squared is 25. 1 over that means we've got 5 to the negative 2, with all this other stuff still outside as an exponent. All right. Well, this isn't looking very pretty, but we can simplify this using some exponent rules. The key here is that we want to keep simplifying things until we have only one base on each side. So for this first one, we can do 4x for our exponent. And then 5 to the 3rd, we can keep that the way it is. This negative 2 gets distributed to the 6 and the 4x. So that's going to be negative 12 plus 8x. Next, we're multiplying these like bases on the right side. We only want a single base of 5, so we're going to need to add these exponents together. That'll be negative 9 plus 8x. And now at this point, we have the same base, so we can cancel those and write 4x equals negative 9 plus 8x. Subtracting the 8x, we've got negative 4x over there. Dividing by negative 4, x equals 9 over 4, or 2.25. This next problem seems really simple at first glance because we've just got these two things, but it's actually quite a bit trickier if you look at the numbers. We have base 3 over here. We have base 16 over here. Now, 16, unfortunately, is not a power of 3, or at least it's not an easy power of 3. There is some crazy decimal that you could raise 3 to that would turn it into 16, but we don't know what that is off the top of our heads. It's probably going to be somewhere between 2 and 3, because 3 squared is 9 and 3 to the 3rd is 27. Anyway, easier way to do this one is to use logarithms. Remember that when you take the log of something with an exponential term, that exponential term pops out as a coefficient. So what we're going to do here is take the log of both sides, and we have to do both sides because otherwise we're changing the balance of the equation. Take the log of both sides, and then that x is going to pop out as a coefficient. Now to get x by itself, we just have to divide both sides by log of 3. Now when you're dividing by logarithms, keep in mind that you are just dividing by a constant. This whole thing is one big constant. So we're going to end up with log of 16 over log of 3. And I really emphasize that logs are constants because a lot of people look at this, and if they've never seen logs before, they're like, oh, I'm just going to cancel out these logs. Well, you can't do that. This log of 16 is one big decimal. This log of 3 is some other crazy decimal. You have to figure out what those decimals are and divide them. For this, we are going to need the calculator. And I usually wait until I have x all by itself before I start plugging things in the calculator. That way I don't have to round off as I go and lose accuracy. So we've got log, here's our log button, log of 16, close the parentheses, divided by log of 3. And optional if you close that last one, equals, so there's our decimal. They said the nearest hundredth they want, so 2.52 is what we're rounding that off to. Here's another one for us to try out. Now this one really looks nasty because we have roots, we have a fraction, but it's not so bad if you realize that you can rewrite this with negative and fractional powers. And it's a good idea to do that before you try taking the log of both sides. So take a sec to rewrite this as base 4 with some kind of exponent. Since 4 is inside this radical, this is really 4 to the 3 over 2x. Since it's in the denominator, this is really 4 to the negative 3 over 2x. So now that we've written that as a single exponent with 4 in the numerator here, we can go ahead and log both sides. That'll give us negative 3 over 2x times the log of 4 equals log of 7. And at this point, we have to do a whole bunch of rearranging. 2 needs to come upstairs to be with log 7. 3 needs to go downstairs along with log 4. And then this negative also has to make it over there. So we have 2 log of 7, that whole thing is going to be negative, divided by 3 log 4. Before you plug this in your calculator, very important, order of operations says that if you just do negative 2 times log 7 divided by 3 times log of 4, if you do all that and write that out in one long string, what's going to end up happening is you're going to end up multiplying these things together, and you'll divide by 3, but then you're going to take that whole answer and actually multiply by log 4. That's not what you want. You want to make sure this multiplication happens before the division happens. So on the calculator, make sure you use a parentheses if you are multiplying things in your denominator. So let's go ahead and write that out now. So here's what I've entered into my calculator, negative 2 log 7 divided by, notice I open a parentheses and then close it with 3 log 4 all inside, and then that will give me the answer of negative 0.94. If you got something else, check your PEMDAS on your calculator. Another thing you could do is do 2 log 7, then divide that by 3, and then divide again by log 4. That's another way to do it.
So at this point, hopefully you feel like you can solve any kind of exponential equation using logs. Pause the video and see if you can solve this one. Alright, so you might have run into some trouble actually trying to solve this, especially if you got an x value and tested it out. The problem with this one is that if you take the log of both sides, we can't do anything about this plus 8. The log of the sum of two numbers doesn't have any special kind of rules. This one, in fact, can only be solved with a calculator. To do that, we're going to graph the left half of the equation and the right half of the equation, and then just find the intersection between the two halves. And this is a technique you can actually use to solve any equation out there. If you already know how to do this kind of thing, pause the video and try it out. Otherwise, follow along. So for those of you following along, here I am in my y equals. I've got y1 equaling the left half, 11 to the x plus 8, and y2 equaling 33 to the x, the right half of my equation. Now I'm going to go ahead and see where these intersect. To use that, I'm going to have to do second trace, and that'll be option 5, the intersection option. Before we do that, though, you need to actually see the intersection in order to find it on your grapher. If you can't see it, you can't use this nifty function. So we need to know approximately where these things are going to intersect before we can even do this. Otherwise, we'll have to use a very large window, and it might take a while. So one clever way to do this is if you plug 0 in for x, that'll be 1 plus 8 on the left side and 1 on the right side. So the left side is actually bigger than the right side at x equals 0. But now at x equals 1, you've got 19 over here and 33 over here. So by the time you go from 0 to 1 for the x values, the right side has already overtaken the left side. That tells us that x equals a number between 0 and 1. So to take advantage of that, we can go to Window, and I can make my x min 0 and my x max 1. And now if I go to Zoom and go down to 0, Zoom Fit, it'll give me the perfect window for these two functions between x equals 0 and x equals 1. So there's my left side of the equation. Here's my right side, and as we can see, it does indeed cross my first equation somewhere between 0 and 1. To find out specifically where that is, we go to second, trace, and then option 5, intersect. We press once for one curve, enter for another curve, and then enter one more time. And that gives us 0.76 if we were to round that off, and I'll just display that right here. So this is how we could solve something that can't be done algebraically. So that's it for this lesson. Until next time, Mr. Sutton signing off.